another thing that we did, which is the whole gravity thing in the Newtonian context. A lot of that is contained in Misner Thorne Wheeler, Chapter 1. Maybe at some time in the next few months, if somebody wants, that we can put together a class where I'll bring in the photocopies of that Chapter 1, and we'll go through it based on what we did in the first 4 or 5 lectures. So again, you'll be able to open up Misner Thorne Wheeler and own Chapter 1. Okay. These are taken from Wheeler. If you draw the up, sideways, and forward in time, okay, so you have something, a ball and a bullet, all right, they're moving. This is the x, y, let's say, right, this is the y direction up, this is the x, this is space, this direction is time, all right, so actually it's moving in 2 dimensions, not in 3 dimensions in space, but we're plotting that in time, all right, so at any instant, what you're seeing is kind of a cross-section. This is the xy plane. At one instant in time, it's over here in the xy plane. At another instant in time, it's like here in the xy plane. Another instant in time, it's over here in the xy plane. All right, you have a ball moving along the xy in time, and a bullet moving along the xy in time. What ought to be the same about these two? Well, we know that the acceleration that both are experiencing is the same. Okay, you shoot a bullet like this, and it's moving. As soon as it leaves the gun, there's no forces acting on it. It's in free fall. It has a certain initial velocity up, so it moves a little bit, but most of the velocity is sideways, right? As it leaves the gun, it's in free fall the whole time. The ball is thrown up in the air, maybe higher, right, but with less speed, presumably, right? But as it leaves your hand, again, it's in free fall. So they're both in free fall the whole time. So both these world lines, okay, are describing particles in free fall. What is the same about both of them? Not the speed, not exactly the direction, but which time? Okay, they both leave, let's say, at the same time, right? They don't land in the same, well, they land in the same point along the, calls it east over here, along this whatever x-axis. All right, the amount of time was different. The ball took more time to get to the same place. Okay. One thing that, a feature of gravity that stands out and that is really central to the discussion that we were having last time is the fact that it's moving along at different speeds, okay? But one thing that is the same about both will be the acceleration. The acceleration of both the ball and the bullet will be the same. G is equal to 9.8, right? How does that come about geometrically? What factor geometrically here can you interpret as the acceleration? What is the same? The second derivative. The acceleration is the same for both. What is the acceleration? It's the second derivative of the displacement with time.
It's the up particular.
Pardon me?
It's only the second derivative of the up
right.
direction.
Okay, the second derivative of the height per time. Okay. Now, how would you see that in the graph? What is the second derivative?
Curvature.
Curvature. So in other words, the curvature of these two world lines ought to be the same. And in fact, if you draw them, correctly, they will roughly be the same. And in the book where I took it, it's multicolored, and it kind of shows you a little bit of this graph, a little bit of this graph, and says roughly they're the same. Okay, now this is the curvature of the world lines in a flat 3-dimensional space-time, 2 dimensions of space, 1 of time. What we're going to be talking about is a curved space-time. You can't draw a graph like this of a curved space-time. You need curved axes, which are impossible pretty much to draw. Okay? But this gives you a little bit of a feeling. You have a world line. You have 2 particles. They're in free fall. Their accelerations are identical. Therefore, the curvature of their world lines in this 3-dimensional flat space should be the same. Okay, another drawing. These are taken from Wheeler. 2 objects moving up and down or moving along the different axes, it doesn't matter. But basically what he's trying to show you is that the curvature of this line will be similar to the curvature of this line, even though the trajectories are different, just like basically it's the other graph.